Yes, students, our point of discussion is the colors of transition series element, and we are focusing on the first transition series and various colors of various ions also we come across. Why variation in color is there, that we have to discuss. But let us revise the thing those we discussed last time. What is the color of Cr plus 3?
Green.
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 Right, it is green. What is the color of Mn plus 2?
Pale pink.
Pale pink.
Yes, it is pale pink. What is the color of Fe plus 2?
Olive green.
Yeah, olive green, or you can say it is a pale green. Similar one metal ion is there, whose color is green only, but little bit dark green compared to Fe plus 2. Which is that metal ion?
Nickel plus 2.
Right, nickel plus 2 also shows the same. Now, last question. Yesterday I committed mistake while telling the color. What was that metal ion and what was its color?
Titanium plus 4.
Very good, very good. Titanium plus 4, I was saying it is a blue or yellow. In true sense, what's the color?
Colorless.
Colorless.
Yes. See, these are the ways by which you could able to remember. I commit mistakes, I remember that. By the way, you also can remember the teacher committed mistake there and that was that metal ion. So when you perform the study at that time, if you could not able to recall, okay, what's the color of vanadium plus 4? Vanadium plus 4, vanadium plus 4, yellow. That you will come to know if you could not recall and you see that color mistake. The next time chances are less that you will commit a mistake. So this is also one way by which you can learn. Anyhow, we have to correlate our study. Anyhow, we should remain in present there while studying. And whatever happens there, that should be like a movie. And that we have to remember. A photo scan will be there, or videos will be there, or audios will be there. With the help of that, you have to understand the study and you have to prepare. Yes, is it clear to all what I said?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Good, good, good.
Yes, sir.
Now various colors we saw. Then why these colors are there? That I answered. Why colors are there? Colors are due to
Unpaired electron.
okay, right. But not always.
Absorption of light.
Right, absorption of the light, electromagnetic radiation, absorption of energy. There are many examples. See, vanadium plus 4, non-electron but colored. Mn plus 7, non-electron but colored. Scandium plus 3, non-electron, colorless, right? Titanium plus 4, non-electron, colorless, right? So electron is needed. In your book, they have mentioned accordingly. But if electron is not there, then color will not be there. Likewise, also we can't say. It depends. So I'm coming to that point. But absolutely, you're right. The color is due to absorption of light. Now, answer for my question. Why is this absorption? Absorption of light for what purpose?
Excitation of electron.
Yes, for electron excitation or electron transition or electron movement. Good, very good. All you are brilliant. If I consider a coordination compound, say ML6, in general, don't get confused. In the two parts are there. Coordination compound is with two parts. What is the one part? One part?
Manganese.
Metal.
Yes, metal ion or generally you can say metal. Here, charges are not represented, but understand. And what's the other part?
Ligand.
Yes, ligands are there. So metal ion and ligand. Let you take any entity, atom, ion, or molecule. They remain with outer portion as electron, and we come to conclusion that color is due to the movement or transition or excitation of the electrons. Which electrons? Metal ion or ligand or both, means ligand to metal, metal to ligand. That we are going to discuss now. I repeat what I am saying. We already concluded that there is a transition or excitation of the electron. But which electrons? In which orbitals? Whether from the metal ion, whether from the ligands, or from both, means metal to ligand or ligand to metal. In case of metal ion now, if I will talk, answer for my question. Outermost electrons, yesterday electronic configuration I represented. Outermost electron in Fe plus 2 or Mn plus 2 or Mn plus 7, Cr plus 3, these metal ions do remain present in which orbitals? Which orbitals? Yes,
D orbital.
d orbitals. So d orbitals are there. How many d orbitals do remain? D is a sublevel. D is a subshell. How many d orbitals do remain? Total how many are there?
5.
Yes, such 5 d orbitals remain. And from our basic concept, all 5 are of same energy. If they are of same energy, then where will they excite? Then one will say d orbital can excite to higher orbital, say s orbital or p orbital. Likewise, expectation may be there, but reality is those d electrons are not exciting. Who are showing color? No, they are not exciting to s orbital or p orbital, higher orbital. They are exciting within d only. How it is possible? I come to that point. If I consider, say, ligands, ligands are vary. It may the water may be the ligand, ammonia may be the ligand, or phosphine may be ligand, arsine may be the ligand. So p orbitals also may be there. Majority p orbitals will remain present on the ligand, but ligand is a complex, no, H2O molecule. Molecule, no, it is. It is not only oxygen atom. As like chloride, fluoride, ions are there only. Their molecules are there. So molecules remains with the various orbitals. And those orbitals within the molecule, those of which type, which symmetry, that we should know. Then only we will clearly understand which orbitals are clearly involved. Not atomic orbitals now, or ionic orbitals. Molecular orbitals will be already involved. So that study we are discussing in detail. But timing consider only the ligand orbital. P orbitals may be there or d orbital, especially p orbitals only to remain. Maybe antibonding orbitals or molecular orbitals in the ligand to remain present. So excitation of electron may possible due to 3 means. The first mean, especially about transition series elements I'm talking about, d to d, d orbital from metal to d orbital from metal. Second type of transition, the metal, of course, d orbital to ligand orbitals, molecular orbital from ligand. And third type of transition possible, ligand to metal. These are the 3 ways of the transition. So what we studied in this point, colors are there, colors are observed, colors are for due to absorption. Absorption is for electronic excitation. Electron is exciting from one level to other level. So which levels are there? The direct answer I had given. Detailed answer you will come to know next year. But timing, remember, is a direct answer. D to D, metal orbital to ligand orbital, or ligand orbital to metal orbital. And when can we see the color? If any wavelength from visible range is absorbed, then we can see the color. So whatever the 5d orbitals are there, those 5d orbitals actually they split in 2 parts. One were 3 and other were 2. It is called as splitting. Splitting of whom? D orbitals in 2 parts. It's called T2G part and it is called EG part. Here you have to just listen. No need to by heart. Total 5 orbitals are there. These are the non-axial dxy, dyz and dxz. Here dx square minus y square and dz square. These are the EG orbitals. These are non-axial and these are axial. Because of their orientation and the approach of ligand, the energy changes. Previously, what was the case? The d orbitals were of the same energy level. No splitting, no gap. About D I am talking about. So D transition would have not been possible. But we are finding color means there's a gap in the d orbitals. There's a splitting in the d orbitals. Now, whatever the splitting I represented, maybe you are finding is difficult to understand. Don't worry about that. Only you understand splitting is there. Next year, why T2G is of low energy, how much low energy, everything you are discussing. You will learn that. But timing, remember, the splitting of the orbital. So if any unpaired electron remain, say in case of the titanium aquo complex, TiH2O6 plus 3. If any unpaired electron remain, then that unpaired electron will absorb that energy. Actually, it absorbs the green wavelength. That unpaired electron absorbs the green wavelength of 500 nanometer wave. That's the wavelength. And this unpaired electron, after absorption, excites to higher energy level because this gap is there. No, this gap is in such a way that it absorbs this 500 nanometer wavelength. When green color is absorbed, the observed color, yes, anybody knows the complementary colors? It is not exactly. Observed color is purple. So titanium aqua complex is purple in color. Yes, do you know what is the color of titanium plus 3? Yes, what is the color of titanium plus 3?
Purple.
Right.
Purple.
Purple, that only I'm talking here now. Purple color. This purple color because that complex absorbs this green color. After green color absorption, remaining colors are reflected or transmitted. Mixture of those remaining colors, that is a purple color, and that we see as what the color for the titanium ion. Titanium plus 3 ions. Could you able to understand what I'm saying?
Yes, sir.
Yes, sir.
Yes. So one kind of transition, one kind of reason for transition is splitting of d orbitals, or type of transition is DD transition. For this, unimpeded electrons are necessary. I think Saurabh previously has answered no, what is the initial condition, or maybe who has answered previously? Unimpeded electron necessary. Somebody answered no. Gauresh was there. Has Gauresh answered at the time? Unimpeded electron necessary, like somebody said no. To find color, what is necessary? Yes, do you know that?
Absorption. Absorption of light.
Yeah, absorption was the answer. But at that time, somebody answered unpaid or necessary. Who said that? Gaurav, no? Yes, Gaurav. Actually, you're right. But for which kind of transition? DD transition. Unpaid on is necessary. Gaurav, are you following what I'm saying?
Yes, sir.
Yeah. But suppose if I take a metal ion, say Fe plus 2, or metal ion, say Mn plus 2, and here ligand orbitals also, the ligand orbitals, energy levels are there. Generally, if you see, Fe plus 2 is related to which ion? Fe plus 2 and other ion combination generally we represent. Fe plus 2 related to, yes, which ion? Ferrous related to ferrous sulfate, ferrous chloride. It can undergo oxidation and can form. Even you take apple, if you cut the apple, oxidation occurs, ferrous ion to remain. So ferrous gets converted to
Ferric.
ferric. That is possible by loss of electron, gain of electron.
Loss of electron.
Right, loss of electron. So my point of interest is here. This Fe plus 2 will tend to give electron, has tendency to give electron to ligand orbitals. So transfer from metal orbital to ligand orbital, that also comes. And that is what the metal to ligand transition. So metal to ligand transition also is one of the way for the, or one of the reason for the observance of color. For that, metal should be in low oxidation state. Ferrous in low oxidation state. Now, this concept will be more clear if you know this. See, I want to talk here Mn plus 7. Yes. What's the color of Mn plus 7?
Magenta.
Yes, magenta color. Okay, it looks purple only, but magenta color is there. Pink color, somewhat pink and purple mix is there. It's a magenta color. Mn plus 7. Now, Mn plus 7 is the highest oxidation state or low oxidation state? Highest. Yes. So it will tend to decrease oxidation state. So to decrease oxidation state, this Mn plus 2 will take electron or will give electron. To decrease oxidation state, electron will be taken or given. Ferrous to ferric, increase in the oxidation state, loss of electron. Now my question is, Mn plus 7, oxidation state can decrease. So if it is going to decrease, then it will take electron or will give electron?
Take electron. Take electron.
Yes, it will take electron. 1 electron, 2 electrons. So reduction. So from whom can it take electron? The temporary exchange is there. It can take electron from ligand. Electron can come from ligand to metal. So that is also the transition. Here, Mn plus 7 actually has how many d electrons? How many electrons are there in Mn plus 7? Manganese, atomic number 25. 3d, 5, 4s2 is an electronic configuration of Mn. I want Mn plus 7. How many electrons will be there in the d orbital? How many will be there?
0.
0. There will be no electron. So electron is not there. Then how it can be colored? It has no electron, so it has tend to take electron, or high oxidation state. Less number of electrons are there. It tends to electron. So it borrows the electron, takes the electron from ligand, and during that transition, electron directly will not come. Electron needs energy to transfer. So for that, light will come for the help, and that particular light will be absorbed, and electron from ligand will come to metal ion. Iron orthophenol complex. If you do the practical dimension, one indicator is there, ferroin indicator. It can show blue color also, it can show red color also. Here there Fe plus 2 remain, and outside orthophenol ligands are there. So electron from metal, Fe plus 2 can go to the ligand. So that is called as. So which two transitions, what I said here, no? M to L and L to M. These transitions are called as, these two are called as charge transfer transition, CT, charge transfer transitions. So students, by this presentation, what I want to emphasize, colors are due to absorption of electromagnetic radiation. Help me now. That absorption is for what?
Excitation of electron.
Excitation of electrons. And that excitation of electrons is possible by three means. Excitation within the orbitals, direct transition. Titanium aqua complex example you can take. Excitation of electron from metal to ligand orbitals, iron orthophenol complex, ferroion indicator. And excitation of electron from ligand to metal ion, potassium permanganate, potassium dichromate, potassium chromate. Many examples you can take. So we have discussed not only the reason for the color, not only the colors, but in detail which orbitals are involved in color finding, that we have discussed. Here the topic or the point, colors of the transition series metal ions and their compounds, complexes, is complete. Is this point clear?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir. Yes, sir.
Now I want to begin next point, that's the magnetic properties, and see what's the good thing I am finding. Nearly all you are with tendency to learn. So your graphs, concept is clear to you. Only memory based you are not studied. Somewhat concept is clear. Am I right?
Yes, sir.
Yeah, that's a learning. So for that, teacher's perspective is necessary. Otherwise, for information data, books are there. You should go through the books or study material. And here discussion we have to perform. Now for this magnetic properties also some insight I need to give it to you. Then concept will be the more clear. Do you know what are the types of magnetism, or what are the different ways by which we can understand the magnetism? Major three are there, further are there, but mainly
Diamagnetism.
yes, diamagnetic. Second
Paramagnetic.
Paramagnetic.
and third,
Ferromagnetic.
brilliant, brilliant, very good. Now diamagnetic material, attraction or repulsion, means magnet is there, magnetic field is there. There will be attraction or repulsion.
Repulsion.
Good. Paramagnetic material, attraction or repulsion.
Attraction.
Good. Ferromagnetic material, attraction or repulsion.
Attraction.
Attraction. I am finding here two-way attraction. So among these two, where there is a more attraction? Paramagnetic or ferromagnetic?
Ferromagnetic.
Right. Ferromagnetic. Ferromagnetic. So how we understand that the magnetism? Suppose if I consider here one magnet, a magnet bar, we represent one as a north pole and other as a south pole, and we show magnetic lines of induction. So don't go on this shape of the diagram. Yes, have you come across such a diagram?
Yes, sir.
Yes, it is what the magnetic lines. Where magnetic line intensity is more, intensity or density is more, near pole or away from the pole. This is magnetic lines of density, you can say. Magnetic lines of induction or intensity of magnetic lines, magnetic field. Where is more? It is at pole or away from pole.
Pole.
Right.
Yes. So this region is there where there is a strong magnetic field, strong, same magnet. But this region is there, this region where there is a weak magnetic field. Pole region is there where number of lines are more, magnetic lines are more, intensity is more. And away from the pole, this region is there where intensity is less, number of lines are less. Means simply, if I draw one line, it has one intensity, density. Similar line, I draw there. Now what I do, I repeat second line, third line, fourth line, fifth, sixth, seventh, eighth, ninth, 10. Now you will understand. The first line is more darker than the second line. Color is same, but repetition is more. Number of lines are more. So number of lines are more here near the pole region. And as you go away from the pole, number of lines will be less. Now about paramagnetic and ferromagnetic, I want to do discussion. Therefore, I'm talking about this point. There is a one rule or there is a one statement. Paramagnetic material moves from strong field to the weak field or weak field to strong field. What do you think? This paramagnetic material moves from weak field, means from center to strong. Means here is a magnet, and if you keep the paramagnetic material here somewhat, then slowly it will go towards the tip, towards the end where strong magnetic field is there. It's a movement from weak field to strong field. Are you following what I'm saying?
Yes, sir.
Yeah.
Yes,
It is a one possibility, means weak field to strong field. And other possibility, it is at end That's a material paramagnetic is end, and that is going from end to away from center. So away from end, or it is coming to center or coming to middle portion. Means it is called as movement from strong field to weak field. What do you think? Or you don't know? Anything you can answer. If question not clear, then also please ask question not clear.
So repeat one more times.
Okay, see, I am considering magnet. This is a magnet. Strong field, strong field. This is a pole region. And here there is a weak field. Here there is a weak field. Are you understanding?
Yes, sir.
Yes, sir.
Yes,
I
sir.
am with one paramagnetic material and I kept paramagnetic material here. I am bringing here. So this paramagnetic material is towards what? The pole. Here, I'm saying, toward the pole. Are you understanding? I am bringing paramagnetic material. So it will move from here to here. It will get attacked here, attached here. Here, less intensity, less magnetic lines are there. So from strong field, it is going to weak field. Is one option. Is it clear?
Yes, sir.
Yes, sir.
Other, I am bringing here that paramagnetic material, but magnet is attracting that paramagnetic in such a way, I am throwing it from here, I am placing it here, but automatically it comes towards the pole. It comes toward the high intensity. It comes toward the high magnetic line, weak field to strong field. So my question is, paramagnetic material moves from strong field to weak field or moves from weak field to strong field. Is it clear now?
Yes, sir.
Yes, sir.
Yes. What's the answer?
From weak to strong.
From weak to strong. Any other answer? If no, then say no. Other students are not replying me, they have no answer.
Strong field to weak field.
Yeah, strong field, two answers. Any last one answer I want.
Weak
One is
to
saying
strong field.
weak to strong. Weak field to strong field is wrong answer. About paramagnetic. Paramagnetic material moves from strong field to weak field. Strong field to weak field. So if I bring paramagnetic material, it will go from here and it will get attracted other way. Is it clear?
Yes, sir.
About ferromagnetic material, reverse is the case. Sorry. In ferromagnetic material, from weak field, the material come to strong field. Means, for example, iron. Means if I here consider tip, pole is there. If I bring here, no, then if I throw the iron, then iron actually should come here, no? It will go here. It will be attracted at the tip. It will be attracted at the end. It will be attracted at the strong field. So actually, it was in the weak field. I'm feeling that attracting magnet is attracting now the iron. And if I release that, it will come here. Means it has a tendency to go from weak field to strong field. So if I place the iron here, it will come here. It was a strong field. Iron is a ferromagnetic material. Therefore, I'm saying. So ferromagnetic material can move from weak field to the strong field, and paramagnetic strong field to weak field. These are general statements. Today, what we have to do, we have to actually understand what magnetism is. Why these things happens. Are you interested to know that?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yeah. Now here few students are there. Let me know how many students are there. 13 students are there. Every student is with different tendency. Few students are there in your class, but they have phobia. Means these lines of teaching, whatever I am giving instruction, no, consider these are the magnetic lines or the teaching lines. Lines of teaching. Lines of magnet. Now I'm a teacher, so lines of teaching you understand. So few are there in your class. Oh, who will attend that? It's a bore. It's better to move here and there, or it's better to sleep. It's better to take a good food, and enjoy. Otherwise, see the serial, see the cartoon, or play the game. So about these teaching lines, they have phobia. It's their nature. It's their tendency. And in case if they attend lecture, if they remain present, then the lines will bombard. Teaching lines, instruction will bombard, and headache will start. Because they are repelling those teaching lines. They don't want to pass those teaching lines. But if any instruction, any information, if any thoughts about trip are there, excursion, if any thoughts about games are there, if any thoughts about entertainment are there, suddenly window will open and lines will pass. Could you able to understand what I'm saying?
Yes, sir.
Yes, sir.
Yeah. So that is what they are not allowing to pass the lines. Likewise, the material also remain. Let the field be. They don't allow the line to pass. They don't allow the line to pass. And few materials are there. Now, amongst you, few will be there. Little we are understanding. Means if I go in the slow speed, one by one, stepwise, or low intensity of instruction, low density of instruction, less number of lines of teachings, is compared with magnetic lines. They are comfortable. And by any means, if I increase the speed of discussion, then they say slow down, repeat. Means, see, don't take it individually, just for understanding purpose. So when I stepwise inform or other angle inform, then yes, now they understand. So when high intensity instruction remain, they want instruction, they love instruction, they like to follow, they like to learn, but strong speed they don't want. So from strong field, they will go to weak field. They have attraction. They want to learn. Are you following what I'm saying?
Yes, sir.
Yes, sir.
Okay. By the way, there remains few students. If I talk slowly, no, they will say, come on, fast, give other instruction. Now this point is over. We understood that point. Go next now. So from weak instruction, from low instruction, low density instruction, they want to move to high density instruction because their caliber to grasp is what more. So they want to go to the high field, ferromagnetic material. From weak field, they also want to learn. But from weak field, they go to the strong field. They themselves move because this is their tendency. They can allow the lines to pass. They can allow the teachings to enter to their brain. As like your natures are there, likewise, materials are also of these three types. This diamagnetic material, they do repel the magnetic field. Magnetic lines, understand? It's a flow. Magnetic lines of any field when remains over there, it's like a flow, you understand? Means we don't consider only as a static. The dynamic flow is there, considerable force is there. As like light passes, light flows, light moves, water flows, water canal flows. Likewise, the flow is there, understand? This diamagnetic material, they repel that flow. Actually, repulsion is not there. They do not allow that flow to pass. And because of that, it causes repulsion. How? I explained that. But timing, remember, diamagnetic material do not allow that flow, do not allow those magnetic lines to pass through it. Therefore, they repel. Paramagnetic material, yes, allows to pass the line, therefore attraction. But tendency of the paramagnetic material to allow to pass the line to some extent or little extent, less magnetic lines are allowed to pass. Therefore, weakly attracted. Paramagnetic material, what we say as weakly attracted. Less number of lines it could pass, but attraction will be there. And third one, ferromagnetic, more lines of instruction they can allow to pass. So strong attraction will be there with the magnetic field. Are these types clear?
Yes, sir.
Yes.
Yes, sir.
One more, last example. Listen carefully. Consider here is a flow of water, stream of water, and I kept my hand there in between the stream, in the flow. What will happen? Hand will be attracted towards water, or hand will be repelled, or no attraction, no repulsion.
Hands will be repelled.
Yeah. Actually, in true sense, a skin or hand and water attraction, repulsion, timing we are neglecting. But because of flow is there and it could not pass through the palm, no? It could not penetrate through that. So if it is not, but flow has a pressure, and because of that, I'll feel my hand is moving out. Intentionally, I have to keep there. I'll find hand is moving out. Likewise, if we want to bring the diamagnetic material towards the magnet, you will feel somebody is there, some ghost is there, something is there in the magnet. It is throwing it out, repelling. That repulsion will find superconductivity. Even a train, complete train, bogie of the train can be lifted by means of this diamagnetism. That's a superconductivity phenomenon. Very interesting phenomenon it is. So that's the power of diamagnetism. Many times hovering of the magnet or magics you are finding, it is because of the diamagnetism. So there's a repulsion. Repulsion means hate, not likewise. Doesn't allow to pass. Means is indirectly repulsion. Flow remains, then there will be also repulsion. So that is what the diamagnetic material do not allow the lines to pass. Now question arises, why diamagnetic materials do not allow the lines to pass? I come to that. Give me some time. Let me complete other portion. About paramagnetic material, it allows the line to pass. Means if I consider such fingers, gaps are there, it can pass, no? So as repulsion was explained here, repulsion will be less or somewhere attraction. To make this concept clear, consider flow of water is there. And wire, do you know wire gauze? In chemistry department, 11, 12, you might have come across wire gauze. Yes or no? I am asking about wire gauze. Do you know? Okay, I show you the picture. Yes. Have you seen such picture, image in chemistry laboratory?
Yes, sir.
Yes, sir.
If I keep that wire gauze, so this central portion is there, no? That's a white portion. That's asbestos coating remains. I'm not talking about that asbestos coating. Just see this. Just wait. The central coating, I am not asking this one. If you remove the central coating, this portion don't consider. White portion don't consider, or partly porous consider because when you use it repeatedly, you know that it become more porous. It doesn't remain that non-transparent. And if I keep that wire gauze in the flow of water, then what will happen? There's a mesh, you know. Here gaps are there. Here gap is there, gap is there, gap is there, gap is there. Could you able to understand what I'm writing here or what I'm showing?
Yes, sir.
So those gaps through which water lines will pass. And because of that, if I have to remove that wire gauze from the flow of water, I will feel some ghost is there. Something is there inside which is attracting that wire gauze. I'll feel attraction. But truly what is there? Water lines are passing, no? And because of that flow of that water line, we feel as if like there is attraction. When you understand the concept, then you feel as if like you have the attraction towards the study. But less number of line pass. And therefore, we say it moves from strong field to weak field. Is that paramagnetic material concept clear? Less number of line passes. Do you understand wire gauze example? Few lines are passing. And if I try to lift it out, no, I will feel as if like some attraction. Could you able to guess that or no?
Yes, sir.
Okay. Will you more clear? Will you more clear when you discuss this ferromagnetic? Now imagine same flow of water and I kept one hollow pipe, hollow PVC pipe, a small pipe you consider, small length. I kept that. So lines are passing, water is passing, water is flowing to that. And if I were to remove that PVC pipe from flow of water, what I need to do? I need to apply more force. Would you able to imagine?
Yes, sir.
It means I will feel as if like there's attraction, strong attraction, more attraction. So while removing that PVC pipe, I need to apply more force, more energy, means it will be more attracted. Wire gauze, less attracted, and simple hand repulsion. So that's the issue. Magnetic line is a flow. These magnetic lines, if pass through the more extent, ferromagnetic. If these magnetic lines pass to less extent, paramagnetic. If these magnetic lines could not pass, it will be the diamagnetic. Therefore, these materials we divide in the three parts: diamagnetic, paramagnetic, and ferromagnetic. Now, question arises: why there is no passage, or little passage, or more passage to the magnetic lines? Answer is in the magnetism. Have you heard the Faraday's experiment? Faraday's law.
Yes, sir.
Yes, will any law don't state, but experiment even if you say, then also will do. Okay, maybe difficult for you. What Faraday did? Do you know magnetic needles? Magnetic needle, how does it remain? Which direction? Yes, magnetic needle remains in which direction?
North and south.
North to south. It's a natural tendency. What Faraday did, he considered one electric wire near the magnetic needle. When current, I say I, current was not pass, at the time it was north south. As soon as current passes, it is found that a magnetic needle deflects, wobbles, changes. I repeat, when current was not pass, magnetic needle was north south. As soon as current passes, magnetic needle is showing deflection. What does it mean? Experiment I told to you, result also I informed to you. What does it mean? When can a magnetic needle will get deflected?
Direction will change.
What direction? Which direction? The direction will change. Yes, right. Direction will change. It's observation. Why direction is changing? When a magnetic needle changes the direction, it wobbles, it moves. When suppose it's a magnetic needle, and if I bring magnet nearby that, then what will happen? Will it remain north-south? A magnetic needle towards that, if I bring magnet, will it remain north-south?
No.
It will deflect. So who deflects the magnetic field? When can needle get deflected? When can needle get deflected? If this wire becomes
Electromagnetic force.
right, it is a magnetism. Electromagnetism, because of electron is there. Of course, electron is there. When it becomes magnet, maybe temporary magnet, then needle will deflect. And it becomes magnet, that wire becomes magnet. Temporary magnet it becomes. It is because of what? Current. What is current? Current is a flow of
Electron.
electrons. So what is happening? Electrons are moving. As electron moves, magnetic needle will deflect. From that, Faraday come to know that if thumb is a direction of current, current is moving in this direction, then curly fingers will represent a magnetic lines of inductions. Here magnetic lines of inductions will be there. And field is there, no? So that field can affect the other field. One magnetic field can affect the other magnetic field, and therefore it gets deflected. So left hand rule, that's a thumb rule I think, our right hand rule you might have studied. If this is a direction of current, then curly finger represents, for left and right both the same thing, curly finger represents the magnetic lines of inductions. That he come to conclusion. He not stopped there. He went on thinking, why magnetic lines came? Because of flow of electron. So if any charge, electron is a charged species, any charged particle or charged species, if moves, if propagate, then magnetic field or magnetic lines will be generated. So let it be the electron or let it be the positron or proton. Any charge, or let it be the positive ion or negative ion. Anything moves, charged particle moves around that, current will be there. So in radiochemistry, nuclear chemistry, you can say different accelerators remain, and the purpose is this one, to control the charges. Or have you heard the experiment, or last year maybe I discussed one particle, I discussed last, I think I discussed with your party, yeah, with your batch. Yes, one particle I discussed. Which particle?
God particle.
To know the origin of life.
God particle.
Right. God particle. And in that experiment, protons were used. Protons. And around that huge magnetic field was there. So you will understand that later on. Time being, any charge species, if it moves, then understand there is a magnetic field. So Faraday concluded electrons are moving, so magnetic field is created. So it concluded it for other charged species also. Let us focus our attention to the electrons. Only electrons are moving. If current passes and electrons are moving, and if I consider simple atom or ion or molecule, answer for my question, what remains the outer portion? Means if I consider the nucleus here, then what remains the outer portion? Yes. What is the
Electron.
outer portion? Right. The cloud you are finding, no? That cloud is of what? The electron cloud model. And my point of interest is this one, electron. Answer for my question. Electron present here, is it at only one place, at one position?
No.
No. It is moving. Electron has two kinds of motions. Which are those?
Clockwise and anti-clockwise.
Okay, no, I'm not talking about. That's a spin motion. And other, as like Earth has two kinds of motions.
Rotational motion.
Rotational, or it's orbital. But don't misunderstand orbital means as like Earth moves around the sun in that way. No, means it's moving from one place to other place. It's random. As like the kinetic theory of gases you have studied. Gaseous molecule. Nobody's there around that. But even though a gaseous molecule now is here, next time will be other way. Randomly it moves. It will not stay at one place. It is a reality. Electron also moves. Don't say orbit in that way, but moment is there. So if electron is with the moment, electron is moving, then why not that electron to be considered as a magnet? Are you following my question? If as per Faraday's conclusion you are saying if electron moves, magnetic field lines will be generated, then why not in atom, ion or molecule where electron cloud, the electrons are there, then those electrons also are not at one place, they are moving. By any means they are moving. If they are moving, then will not they with the magnetic moment? Will not they be like a magnet? Is it clear?
Yes, sir.
Yes, it is. The answer is yes. Electron is a magnet. Electron is a tiny magnet. If one electron has this spin, so it has one magnetism, and other electron is with this spin, and they're pairing. It is with other magnetism. So magnetism caused by one electron and magnetism caused by other electron will cancel, will nullify in opposite different direction. Therefore, net magnetism will be zero. To that we say diamagnetic material. But if there are unpaired electrons, then magnetism is there. Unpaired electrons, I'm saying. Few lines can pass. We can say it's a paramagnetic material. But when many unpaired electrons are there, large number of unpaired electrons are there, so magnetism, large magnetic lines can pass. Too many neurons are there in the brain. Brain is well developed. Brain went to wisdom level. Large magnetic lines can pass. It is ferromagnetic material. So at the beginning, I told you general aspect. Okay, only 1 minute. General aspect. Now I am telling you some particular aspect. Magnetism is due to the tiny magnet, and a tiny magnet is none other than electron. If the tiny magnet is magnetism in one direction, other tiny magnet magnetism in other direction, and if they cancel, no magnetic moment. Magnetic moment mu is equal to 0 for diamagnetic material. Magnetic moment mu will be positive for paramagnetic material. For ferromagnetic material, again, it will be positive, but more magnetic moment. That is called ferromagnetic material. Likewise, materials, not only elements, not only metals, anything we can categorize in this magnetism, and is one of the important properties to study the compounds. Therefore, it is included. So, students, today I discuss you what that magnetism concept is. Base of magnetism I covered. Next lecture we will discuss this magnetism for these transition series elements. Is it clear?
Yes,
Yes,
sir.
sir.
Yes. Anybody has any doubt now? Any question?
No, sir.
No. So, students, shall we stop?
Yes, sir.
At least voluntarily reply. It's a good time for you. Okay, good, good. Okay, fine. I stop the recording and I declare here today's session is over. Quit now.